Hello, pre-calculus. Okay, so we have been talking about solving equations with trigonometry, and today we're going to kind of shift gears a little bit. We're still in the same uh, world. We're going to talk about evaluating inverse trig functions. So we've already been doing this a little bit as we solve equations. We use inverse trigonometry to find out what our theta is equal to, our x is equal to. But what we're doing now is we're moving on to just evaluating. Instead of solving for x, we're going to be evaluating for x. So that's what these notes are here today. Sorry, I realize I'm going to be rocking back and forth. I'm standing up instead of sitting down, which means I'm going to, sorry if that's distracting. Just, I don't know, push me off to the side. Okay, so evaluating inverse trig functions. So the first thing we should do is we should remind ourselves what inverses are. So without writing this down, just think back to when we talk about inverses, and you've talked about inverses in other classes before. So an inverse is when you take the input and the output and you switch them, right? So you take the x's and you make them the y's and you make them the x's. So it's just a little switcheroony, right? So there's a term for this. Inverses are called, I don't know if you remember this term, one-to-one functions. And basically what that means, and you don't necessarily have to write all of this down, this first little bit, this is just kind of a recap. But basically what this means, if you have a function f of x, and maybe f of x looks like 1, 2, 3, 4, those are my inputs, 5, 6, 7, 8, those are my outputs. Then the inverse function of that would be with a little -1 up there. So the inverse function of f would be x and y. I would just, like I said, just switch the x's and the y's. So all of my x values would be 5, 6, 7, 8. And my y values would be 1, 2, 3, 4. So the one-to-one function basically means that each input has exactly one output. So this is different than just a regular function, because a regular function says, oh, every input has a unique output, like there are no repeating x values, right? In a one-to-one function, not only are there no repeating x values, there are also no repeating y values, right? So nothing's repeating. And the reason for that is because we're doing a little switch. So if I have repeating y values, and then I make those y values the x values, now I have repeating x values, and it's not a function. So that's what we mean by one-to-one functions. So that's how you do it with a table, right? That's how you see if a function is one-to-one looking at a table. On a graph, do y'all remember how you find out if a function is one-to-one on a graph? Like if you can make an inverse function from it on a graph. I'm going to tell you if you don't remember. We use the, you're gonna be like, oh yeah, we use the horizontal line test. And so remember what the horizontal line test is, just like the vertical line test, we draw a horizontal line through the graph, and if it impacts, or if it touches the function more than once, then it's not a one-to-one function. Because when we switch our x's and our y's, that means we're gonna have repeating x values, and I can't have that. So here's the sad thing about periodic functions. There are not many sad things about periodic functions, but here's one of the sad things about periodic functions. When I draw a periodic functions, it becomes pretty obvious pretty quick that they are going to absolutely fail the horizontal line test, right? That one hit 4 times. That's very, 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 very faily on the horizontal line test. So what I'm going to write down here is periodic functions don't pass the horizontal line test unless, okay, there, oh, you knew there was a, there's a but, unless we restrict My handwriting is terrible. Let me try to make this just a little bit nicer. Unless we restrict the domain. Restrict the domain. So if we say, okay, we're just talking about this piece of a periodic function, then I can definitely say, oh, I could have a one-to-one. If I just like select, like, for example, like from here to here, like in that box, that would totally pass the horizontal line test. It only hit once, right? So that's what we're going to do. We're going to restrict the domain when we're finding inverses. So we're only dealing with a piece of each periodic function, okay? This restricted domain, these, what we're going to call these, are called principal values. So that's the word I'm going to use a lot, principal values. So that is just the restricted domain that makes each periodic function able to be an inverse, right? So let's take these one at a time. We're going to look at sine, cosine, and tangent. Those are going to be the three principal values that we look at. Sorry, my cat is running around over there. Just want to make sure she's not getting into something that she shouldn't be. Okay, so let's start with sine. So I'm just going to sketch a sine graph here. I would love for you to do this in your own notes. It's good practice. In fact, what you should do is pause this, sketch a sine, like super sketchy, like a very rough sketch. Like don't even put labels on the graph. But just sketch the sine graph just so you can kind of jog your memory of what a sine graph looks like. So I'm gonna do it on here, but I think you should pause and do it on your own. Okay, so here we go. I'm gonna draw it my own self. Thank you, iPad, for making my lines so straight. Okay, so I know a sine graph for me starts right at the origin, so I'm gonna put a point there, and then I'm gonna put, we're gonna say that that's 1. I know I told you not to label your axes. These are just my kind of like top and bottom. And then it's gonna go like the, oh gosh, I'm gonna do that again. It's gonna go like, that'll work. It'll go like that way. And then it's a rough sketch. It's a rough sketch, y'all. It's gonna go like, oh my God. Okay, let's just stop while we're ahead. Okay, so this is our sine graph. And as we just saw up above, this is not gonna pass the horizontal line test, right? So what we need to do is restrict our domain. So let's figure out what piece we want to use. Now, I would say we wanna stick close to the origin, because the origin is where, as it suggests, that's where like the beginning of our function is. If you had a beginning, this is like where we're starting at. I haven't transformed anything at all. I'm starting at the origin. So let's start here. And what I want you to do, as I'm drawing, I'm going to start just highlighting the function. And I want you to tell me as soon as you think that I would not pass the horizontal line test anymore. So if I started here and I went up and up and up and up and up and I hit here, and then as soon as I start coming back down, boom, I failed the horizontal line test, right? So that means that what I want to do is I want to stop right up at the tippy top right there. And if we think back to our unit circle, when the sine value is exactly 1, that value right there is pi over 2, right? Now, I can't go any further. I'm going to fail the horizontal line test because I want to stick close to the origin. So let's just go back the other way. So I'm going to go back this way. And as soon as I take that curve and start going up, boom, I have failed the horizontal line test. So I can only go down to right there at the very bottom, -1. And if we think about where that happens on the unit circle, that is going to be at negative pi over 2. So y'all, this is the restricted domain. These are the principal values for the sine function. So the way that I'm going to write that is, oh, where do I want to put that? Sine is going to be negative pi over 2 to positive pi over 2. Those are my principal values. So I kind of squeeze that in there a little bit. If we're looking at a unit circle, let me draw a little unit circle over here. Hectocircle, yeah. Y'all, I'm not gonna lie, drawing on an iPad is pretty fantastic. If we're looking at a unit circle, if I wanted to look at what angles this was talking about, so I'm starting at 0, which is right there, right? And then I'm going all the way up to pi over 2, right? And then I'm coming back down to negative pi over 2. So all of these angles right there, those are the principal values for sine, right? Negative pi over 2 to pi over 2. The trick to this is making sure that you remember that these down here are negative angles. This isn't like 7 pi over 4, positive 7 pi over 4, and positive 11 pi over 6. These are negative angles, right? So I'm dropping down. So those are my principal values for sine. So y'all, if I asked you to do, let's just do a quick example. Let's say I wanted to evaluate, let's say evaluate the sine, the inverse sine of 1/2. So looking at our principal values, let's draw our tiny little unit circle. I always want you to draw a little diagram. It's very, very helpful. What angle is the sine value 1/2? Where is the sine value 1/2? So on my little tiny unit circle here, I'm gonna be like, okay, sine is y. Where is the y value 1/2? That's right here at that angle, which is pi over 6. Y'all, I also know, according to what I just discovered up there, my principal values for sine go from negative pi over 2 all the way to positive pi over 2. So does pi over 6 fit into those principal values? You bet your boots it does. So I can just say, hey, pi over 6 is my answer. I don't need a solution set around this, right? Because I'm not solving, I'm just evaluating. I'm just saying, hey, what is another way? What is an equivalency to this expression? So I'm just evaluating, I'm not solving for x. There is no x to solve for, right? So be careful there with that. Let's do another example. Let's say I wanted you to evaluate the inverse sine of negative rad 3 over 2. Evaluate the inverse sine of negative rad 3 over 2. So let's draw our little tiny unit circle diagram over here. So where is this? That's not even close to straight. That's fine. So when sine is negative rad 3 over 2, where is that happening? So sine is the y value, so I'm dropping down. So that is happening down here, and that is 5 pi over 3. Now, I forgot to mention this on the last example that we just did. Sine is also negative rad 3 over 2, over here at 4 pi over 3. Kind of like over here, if we had said, where is sine 1/2, it also happens here at 5 pi over 6, right? I don't even have to worry about that. That's the thing with principal values. I can't have two answers, because then if I had two answers, that means it wouldn't be an actual inverse. It's different when I'm solving, and I'm going to write this out in a second. We're only going to have one answer when we are evaluating, right? Because we have a very restricted domain in order to be an inverse. So different when we're solving. Don't take this into your solving world. This is just for evaluations, right? So be careful with that. This is when you type in on your calculator, when you use your calculator to find an inverse trigonometric function, it only gives you one answer, right? It doesn't give you a bunch of different, like if you typed in this one, the inverse sine of 1/2, if you put that to your calculator is only going to spit out pi over 6 or 30 degrees. It's not even going to mention 5 pi over 6. Not even whisper, because your calculator is very affixed into that restricted domain of those principal values. Crazy. Sorry, my cat is, distracting. So let's go back over here. I digress. So we're evaluating the inverse sine of negative rad 3 over 2. And there are two places on the unit circle that happens, down here at 5 pi over 3 and down here at 4 pi over 3. So remembering my principal values are negative pi over 2 to positive pi over 2, I know that I'm not even going to worry about 4 pi over 3. That's not my principal value, so I'm not even going to worry about it. Problem is 5 pi over 3 my principal values. If I look up here, 5 pi over 3 is, where's 5 pi over 3 at? That is happening somewhere around here, right? That is not part of my principal values at all, right? No, it's further than that. Where's 5 pi over 3? 5 pi over 3 is right. I can't, oh my gosh, 5 pi over 3 is like right there. It doesn't matter. It's outside of the range of my principal values. So remember, what you have to remember, this quadrant 4, these are negative angles. So what is the equivalent angle of 5 pi over 3 if I was swinging down to be negative instead of going all the way around to get to 5 pi over 3? How many negative radians is that? If you were saying negative pi over 3, you were exactly correct. That would be the correct inverse of negative rad 3 over 2, negative inverse sign of negative rad 3 over 2. Okay? Now, I want to make us a quick note before we move on to cosine. I want to make a very quick note, and I would love for you to write this down just to kind of remember it. Bing, bing, bing. When you are solving, you need to find all possible answers in the given domain. So the last 2 days, we have been doing solving of equations. And like one of our questions on the worksheet yesterday had like 12 possible answers, right? Because my domain was all the way from 0 to 2 pi, right? So whatever that domain is, give me all of the possible answers, right? For evaluating, when you don't have an equal sign, you're just looking at an equivalency, and maybe I should specify evaluating, there is no equal sign. What you want to do there is use principal values for inverses. So that means that you are only going to have one answer, right? Because your domain is very restricted. So essentially it's the same. You're operating within a given domain. Your domain is just much, much smaller than 0 to 2 pi, right? It's just that little section in the middle there. Okay, y'all, let's talk about cosine. Let's look at principal values for cosine. So I want to do the same thing. I am going to sketch like super, super rough sketch a graph of cosine. I would love for you to pause this and sketch it on your own just to make sure that your math brain is still there and you still have some familiarity with these graphs. So you go ahead and do that. I'll do mine right here. Okay. So cosine for me starts up here at +1. And then my bottom limit is -1, and I know it's gonna go like, oh my gosh, I can't, it's like I can't, maybe I should turn it. I can't draw, yeah, there we go. Okay, yikesers. That'll work. It's a sketch, y'all. It's a rough sketch. And then, oh my gosh, I like sneezed at the end of that. Okay. Okay, I mean, it's not great, but it'll work. Okay, so for cosine, we're gonna do the same thing where I'm gonna trace on this and we're gonna see how far I can go. And we wanna start with just the cosine function, which means we're starting on the y-axis, as close to the origin as we can get, right? So I'm gonna start right here, and then we're gonna go, let's just go forward. So I don't have any, I'm still passing the horizontal line test. So now when I start turning up, that's when I stop passing the horizontal line test, right? So it's all those values. Now, let's see, that is, when is cosine -1? That happens at pi. So here's the thing. I have cosine starting here at the origin, which is 0, going all the way to pi. I don't need to go backwards at all because I have already taken care of all of these values, right? There's nowhere else I need to go to take care of all of the y values that I need to hit that are going to be in this function. So I'm done. Those are my principal values for cosine. So I'm going to say that is between 0 all the way up to pi. So those are the principal values for cosine, from 0 all the way up to pi. And then I'm going to draw a little unit circle right here so we can have our unit circle to look at. So 0 to pi, so 0 is right here, and then pi is right there, so 0 to pi. Those are my principal values for cosine. Good thing about cosine, I don't have to deal with any negative angles, right? So I don't have to remember any of that. I just need to remember, hey, only between 0 and pi, I'm not going to look at anything else out of those, out of that domain, right? Okay, so let's do a couple of cosine examples real quick. So riddle me this. I would love for you, I'm going to write 2 on here. I want you to try to do these, pause them, and do them. So evaluate the inverse cosine of rad 2 over 2, and then go ahead and evaluate the inverse cosine of negative rad 2 over 2. So go ahead and pause this, do those on your own, and then come back and I will work on them over here. So pause. Okay, welcome back. I don't know if you paused or not. Maybe you didn't. I don't know. So here we go. I'm going to look at my little unit circle here, my little sketch. And rad 2 over 2, so cosine is the x value, so rad 2 over 2 happens right here. It also happens right here, positive rad 2 over 2, and that is pi over 4 right there. But thinking principal values, the principal values are up here, so I don't even need to worry. This was 5 pi over, nope, not 5 pi over 4, that was 7 pi over 4 down there. 7 pi over 4 down there. I don't even need to worry about that. Did I get that one wrong up there? No, I didn't. That was 5 pi over 3. Okay. I don't even need to worry about that 7 pi over 4 because it is not within the principal values, right? So the only guy I need to worry about is pi over 4. Is that within my principal values? You bet your boots it is. So the inverse cosine, the angle where the cosine is rad 2 over 2 is pi over 4. Donezo. Let's look at this guy. I'm gonna go ahead and sketch in my principal value area, just kind of do a little shading, just so I know what I'm looking for. So negative rad 2 over 2, where is cosine, the x value, negative rad 2 over 2? So that happens right here at 3 pi over 4, and then it also happens right here at 5 pi over 4. 5 pi over 4 is not in my principal value, so I'm not even gonna worry about it. 3 pi over 4 is my principal values. I don't need to do any fancy math. That is it. Cool. Okay. Hopefully there are no questions. If there are questions, this is a recording, so I can't hear you. So email me, I guess. I don't know. All right. The last one I want to talk about is tangent, and then we're just going to do one more thing, and I will be done. So pause this again. You know what I'm going to say. Pause it. Go write, like sketch a little tangent graph on your own, and then come back and check it out with me. So pause, and then come back. Okay, so the tangent graph looks like rough sketch, okay, like that. And then I know I have an asymptote. Let's draw a better asymptote, like so, and then that happens again with another asymptote, and then it happens over here. Nope, it happens over here too. That's another asymptote. Gracie, come on. Okay, so same thing for finding our principal values. I would like to start as close to the origin as possible. I want to do just the tangent graph, not the tangent graph, transformed, stretched, shifted up, down, side to side, just the tangent graph. So we're going to start right here. So if I follow the function up, I'm still passing the horizontal line test, still passing the horizontal line test. I can go all the way up to that asymptote. And remember that asymptote happens at pi over 2. So I can go all the way up to the asymptote and still pass the horizontal line test because I'm not turning back down, right? Now, I could jump ahead to the next asymptote and start down here. Oops. Start down here, but I want to remember I'm trying to stay close to the origin, so I'm actually going to go back the other way. I'm still passing the horizontal line test. I'm not crossing anything, so all of that green highlighted stuff between those two asymptotes, and this one right here is negative pi over 2. All of that green highlighted function passes the horizontal line test beautifully, so that's going to be my restricted domain for, Gracie, come on, for the tangent graph, right? So let's go ahead and write, it's gonna be negative pi over 2 is less than theta, which is less than or equal to positive pi over 2. So on our unit circle, y'all, boom. On our unit circle, that is going to be negative pi over 2 starts down here all the way up to positive pi over 2. So it's going to be this section right here. Can y'all hear her? I hope you can't hear her. My cat's just like scratching on the door over there. She's being a turd muffin right now. So again, just like with sine, remember these down here in the quadrant 4, those are negative angles. So that is super, super important. Those are not going all the way around. Those are negative angles, right? So be very careful with those. So here's the deal. Sine and tangent have the same principal values, negative pi over 2 to pi over 2, and then cosine has 0 to pi. Those are the principal values right there. Play shop. Stop it. You don't need to go up there right now. I'm sorry that you had to hear me scolding my cat. Okay, so let's do we're going to do one example for tangent real quick. So if you could evaluate the inverse tangent of 0, I'm going to give you a nice easy one here. So let's look at our unit circle. So tangent, remember tangent is, let me go ahead and highlight my principal values real quick. So I'm looking for something in that area. So remember tangent is sine over cosine. So I'm looking for a time when sine over cosine is 0. So what that basically means is I'm looking for a time when sine is equal to 0. Because if cosine was 0, that would be undefined, right? So I'm looking for just when the sine is 0. So that happens, sine is the y value. So that happens right there at 0. It also happens over here at pi, but that is not in the principal value, so I'm not going to worry about pi. So my only answer here is going to be 0. And again, you don't need a solution set. You can just write it out because that's what we're doing. That's what we're doing. Okay, y'all, that's principal values and finding inverses. I just have like 2 more examples. Yeah, we're just going to do 2 more examples of things that have to do with your homework. There's another Go Formative assignment. If you turned in your Go Formative assignment by Wednesday night, by Tuesday night, I went through and gave feedback on most of those. So you have another Go Formative assignment that goes with this set of notes. So go do that because these are a little tricky and I just want to make sure that you have them. Okay. So I'm going to do just a couple of examples of situations that may seem easy, but I want you to have caution, right? So here we go. Evaluate the following. Can you evaluate the inverse cosine of the cosine of pi over 6? That's right. It's inverse function on function action. So remember, y'all, inverses and their functions and their inverses, they undo each other, right? That's why we can say like multiplication is the inverse operation of division, right? So one of them undoes the other one. And so this is what we did with, when we were proving inverses and we had compositions where we would take like f of f inverse of x and the f and the f negative 1, the inverse of f, would undo each other and you would be just left with f. So this is very, very similar, but there's a catch. So what I'd like us to do here is actually like roll through this. So let's draw a little unit circle. So pi over 6 is right here, right there. So that the cosine is the x value, right? So the actual cosine of pi over 6 is rad 3 over 2, right? So what we're trying to find here is the inverse cosine of rad 3 over 2. Now, using what we just did above with all those principal values, we know that cosine has principal values from 0 to pi, right? So we have to make sure that whatever our answer is, it's between 0 to pi. In this case, it does happen to be just pi over 6. So that works out beautifully. So essentially, this inverse function and the original function just did each other in, cancel each other out. And we're left with just the input. It's not always that easy. Let me show you an example when it's not that easy. So let's evaluate the inverse sine of the sine of 5 pi over 4. So I don't want you to see this on a test and immediately jump and just say like, oh yeah, this is so great, this is so easy, those get rid of each other, the answer is 5 pi over 4, and then run away, because that's not correct. That is not the answer. So be careful, be careful, be careful. So let's draw our little unit circle over here. Boop, boop, boop. So 5 pi over 4, where's 5 pi over 4 at? 5 pi over 4 is down here. So the sine value there, sine is the y value. So the y value there is negative rad 2 over 2. So what I'm actually trying to find is the inverse sine of negative rad 2 over 2. The problem with this 5 pi over 4 business is that my principal values for sine are over here, right? 5 pi over 4 ain't over there. So I need to find an angle where the sine, the y value, is negative rad 2 over 2, that is actually in the principal values. So what I can do, what do you want from me? What do you want? This is my cat. This is who's causing all the trouble right now. I don't know why she's going so bananas. Why don't you just hang out for a second? Okay, so the other place where where the sine value is negative rad 2 over 2 is going to be right down here at 7 pi over 4, right? The problem with that is 7 pi over 4 is not in our principal values, right? Because what do we know about this quadrant 4 when we're talking about principal values? Hopefully you remember that those are negative angles, right? So what is the equivalent negative angle for 7 pi over 4? If we were dropping down, instead of going all the way around, we would end up with negative pi over 4. And that, my friends, would be your answer for this situation. Apparently she just wanted some attention. Okay, y'all, that's it. The moral of the story with all of this stuff is please, please, please be careful, be thoughtful when you are solving, when you are evaluating rather, because there's you just need to pay attention to those principal values. Okay, so there's a GoFormative. Go check that out. I'm also going to post a little worksheet with some extra practice problems on there. So try those out. And yeah, that's it. Holler at me if you have questions. You can go to the meetings, the Zoom meetings for classes if you have questions. Otherwise, peace, love, math, etc., etc. All right, bye, y'all.